Hello, everyone, and welcome to the lecture on chemical reactions, balancing equations, and stoichiometry. This reaction is showing zinc and iodine reacting to produce zinc iodide. Notice that we start with two solids. Zinc is a solid and iodine is a solid, but in the products, we're seeing a gas being evolved as well as a solid being formed in the evaporating dish. According to the law of conservation of mass, the mass of the reactants we start with is going to be equal to the mass of the products. We need to capture and measure the mass of that evolving gas as well as the solid that's in the evaporating dish in order to determine what the mass of the products are in total. Once we do that, we find that we have the same mass of products as the mass of reactants that we started with. We're going to cover several different types of chemical reactions in this lecture. Combination reactions, in which we have two reactants that are going to form one product. Decomposition reactions, in which we have a compound that's going to decompose into simpler substances. A single replacement or single displacement reaction, in which we have one elemental atom that's going to displace an elemental atom of similar oxidation state from a compound to form a new compound. A double replacement or double displacement reaction, in which we have two compounds that are going to switch elemental atoms of the same type of oxidation state to form two new compounds in the product. Combustion reactions, where you have a fuel and oxygen reacting to form CO2 and water, and also a redox reaction in which one species loses electrons while another species gains electrons. In the combination reaction, we have a single product produced from two or more reactants, and you can see in this generic reaction that X reacts with Y to form the compound XY. The reactants in this type of reaction can be ions, elements, or compounds, but the product is always going to be a compound. We have this real combination reaction where you see H plus and OH minus reacting to form the compound H2O. In this case, we have ions reacting to form a molecular compound. The decomposition reaction has a single reactant that's converted to two or more simpler substances in the product. And so the generic reaction shows XY, a compound, being decomposed into simpler substances X and Y. The reactant is always going to be a compound in a decomposition reaction, but the product could be ions, could be elements, or could be a compound or more than one compound. In this real reaction down here, you can see that we have water, H2O, being decomposed into the simpler substances from which it was formed, H plus and OH minus. The single displacement or single replacement reaction is where an atom or a molecule displaces an atom in another compound. So in this generic reaction, we can see that X is going to displace Y from the compound YZ. In the products, you see Y is now by itself, and we have a compound formed XZ. In the real reaction, we see that iron is reacting with copper sulfate. Iron will then displace the copper in the copper sulfate, and in the products you can see we have copper by itself now, and we formed a new compound, iron sulfate. If X is a nonmetal, then X is going to displace Z. Remember, nonmetals have a negative oxidation state. And so if X displaces a species in the compound that it's reacting with, it's going to displace that species that also has a negative oxidation state. So X will displace Z in this generic reaction, and you can see in our products, Z is now by itself, and X has formed a compound with Y. In the real reaction that you see here, we have fluorine reacting with sodium chloride. Fluorine, being a nonmetal, has a negative oxidation state. So it's not going to displace sodium with a positive oxidation state. Fluorine is instead going to displace chlorine that has the negative oxidation state. In the products, you can see that we have chlorine and sodium fluoride is our new compound. In a double displacement reaction, we have displacement of two substances, and we have at least two compounds in the reactants. Again, it's going to be the positive oxidation state species that will replace another positively charged oxidation state in another compound. So in this generic reaction, we have A displacing B. In the products, you can see that A is now paired with Y in a compound, and B is now paired with X in a compound. If we look at this real reaction between barium chloride and silver nitrate, barium, having the positive oxidation state, will switch places with silver, also having the positive oxidation state. And in the products, you can see that barium is now formed a compound with nitrate, giving us barium nitrate, and silver has now formed a compound with chloride, giving us silver chloride. We can also have double displacement reactions that are categorized in another way. They may be categorized as an acid-base reaction. In this case, we have an acid reacting with a base. If it's a strong acid and a strong base, it's always going to form a salt and water. In the generic reaction, we have AY reacting with BY to form BX and AY. Now think about this. Both A and B are the least electronegative elements, so they both have a positive oxidation state. And so it will be these two species that will switch places. So the A is now going to form a compound with Y, and the B is now going to form a compound with X. If we look at the real reaction between hydrochloric acid and sodium hydroxide, we see that hydrogen, being positively charged, is going to change places with the sodium, which also has a positive oxidation state. That means that in our products, we're going to see sodium now pairing with chloride in NaCl, and we'll see the OH here in the reactants pairing with the hydrogen here in the reactants. Remember that water is actually HOH. So this is where we see the OH from sodium hydroxide now forming a compound with the hydrogen from hydrochloric acid to form water H2O. Combustion reactions occur when a fuel, and our fuel in this case is butane, reacts with O2 gas to form CO2 and water. You can always recognize a complete combustion because you will always have a fuel reacting with O2 to form carbon dioxide and water in a complete combustion. In a redox reaction, we have one species which is oxidized. That means that that species has lost electrons. We have another species which is reduced, which means that that species has gained electrons. You can remember this with this acronym oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Let's take a look at the redox reaction at the bottom of the screen. Now keep in mind, this is not just a redox reaction, this is a single displacement reaction because the copper is going to displace or replace the zinc and pair with the sulfate to form a new product. If we look at the oxidation state of copper, we see that it's neutral. Anytime you see an elemental atom that is written just like you see it on the periodic table, its oxidation state is going to be 0. If we look in the products, we know that sulfate has a 2- charge. That means that copper has to have a 2+ oxidation state for charge neutrality to have occurred in forming copper sulfate, copper 2 sulfate, essentially. Copper then went from a 0 oxidation state to a 2+ oxidation state. In order to do that, copper had to lose 2 electrons. And so copper has been oxidized in this reaction. If we look at zinc, again, we know that sulfate has a 2- charge, so the zinc has to have a 2+ oxidation state for charge neutrality to have occurred when this compound was formed. If we look at zinc in the products, it is neutral. So zinc went from a 2+ charge to a neutral charge, meaning that zinc had to gain 2 electrons, and so zinc was reduced. There's some important information that we have to discuss before we can move forward in terms of looking at reaction equations. Number 1, chemical reactions occur when bonds between the outermost part of the atoms are formed or broken. So what are we talking about with that statement? What we mean is we're talking about the valence electrons. And so we're talking about the valence electrons and the valence shell. So that is the outermost part of the atom, and we're forming and breaking bonds that are associated with valence electrons. Chemical reactions involve changes in matter. And so if you think about the first reaction that we looked at, zinc and iodine were both solids, and the products evolved gas. So when we formed the zinc iodide, we evolved some gas. That was a change in the state of matter. The making of new materials with new properties is something you've already learned about. And if we look at the zinc iodide reaction, the zinc was a solid, the iodine was a solid. When we formed the product zinc iodide, again, we evolved gas. And so we made a new substance that had properties that were different from the properties of the elements that it was originally formed from. Can also have energy changes. One of the energy changes is referred to as endothermic. In an endothermic reaction, we have energy being absorbed. And so if you're holding a reaction vessel with an endothermic reaction occurring, the vessel is going to feel like it cools down. We can also have exothermic reactions, and if you're holding a reaction vessel of an exothermic reaction, you're going to feel that vessel heat up because energy is released in an exothermic reaction. Symbols represent elements. So going back to our first reaction we talked about, zinc is a symbol that represents an elemental atom of zinc. I2 is a symbol that represents a diatomic molecule of iodine. Formulas describe compounds, so ZnI2 represents zinc iodide. That's a chemical formula for this compound. All of this you were already familiar with. We've already covered this in the class. So all of these points are points that you already know. What we're going to start focusing on is how chemical equations now describe a chemical reaction. The parts of the chemical reaction equation include the reactants, which are shown to the left side of an arrow, and the products, which are substances shown on the right side of that arrow. A plus sign separates substances on the same side of the arrow, so separates reactants from one another or separates products from one another. And the arrow actually indicates the direction that the reaction is read, and we say that the arrow means yields, forms, or produces. So for example, carbon reacts with oxygen to produce carbon dioxide, and this reaction is showing a forward arrow, meaning that we're always looking at CO2 as being the product and carbon and oxygen as being the reactants. Grilling charcoal is basically carbon, which reacts with oxygen to yield carbon dioxide. The purpose of chemical equations is to depict the reactants and the products, and also their relative amounts in a reaction. So in this particular reaction equation, we see that 4 solid aluminums react with 3 gaseous oxygens to form 2 solid aluminum oxides. The numbers in front of those reactants and products are called stoichiometric coefficients. So the 4, the 3, and the 2 are all stoichiometric coefficients. If we have an invisible coefficient, then we assume that it's 1. The letters that you see in parentheses as subscripts are S for solid, G for gas, L for liquid, or AQ for aqueous, which is telling you that that substance is dissolved in water. The principle of conservation of mass, which is also called the law of conservation of mass, tells us that there are no detectable changes observed in the total mass of the substances involved in a chemical reaction. Because of the principle of conservation of mass, an equation has to be balanced. It must have the same number of atoms of the same kind on both sides of the arrow. Now, students often get confused about this because you're thinking about going camping, maybe, for example. You throw these 2 heavy logs on the fire that maybe you had to drag over there because they were too heavy to pick up. And then after they burn, you have this lightweight pile of ashes. But you have to remember back to the first reaction that we looked at with zinc and iodine. When we formed zinc iodide, there was gas evolved, a purple gas evolved. In a lot of reactions, there's an evolved gas that we have to capture. And once we capture that evolved gas and we weigh the solid that's also remaining and any liquid vapor that has escaped, that's when we'll know the total mass of all of the products. And we can compare the mass of the products to the mass of the reactants that we started with. In both cases, we need to have the same mass, and that's what we find in every experiment that we measure. Remember, we have the same number of atoms of the same kind on each side of the arrow because all carbons have the same atomic mass units, all hydrogen atoms have the same atomic mass units, all sodium atoms have the same atomic mass units, and we could go through the entire periodic table making this argument. When we're balancing a chemical equation, you can add coefficients in front of the compounds to balance the reactants with the products, but you cannot change the subscripts. Remember that changing the subscripts will change the compounds. The subscripts are determined by the valence electrons and the resulting oxidation state that allows each elemental atom to have the electron configuration of the Nobel gas that's closest to it. And so we achieve charge balance when we're forming a chemical compound, or if we're forming a polyatomic ion, we achieve the charge that's associated with that ion by allowing all of the atoms to have the electron configuration of the Nobel gas that's closest to them. So bottom line is, when we balance, there are 2 different chemical situations here. The first situation is that we're balancing a chemical formula. When we balance a chemical formula, we use subscripts. And that tells us how many elemental atoms we're going to have in order for each of those elemental atoms to have the Nobel gas configuration that is closest chemically to that atom. The other balancing is of a chemical reaction equation. When we balance a chemical reaction equation, we use stoichiometric coefficients. Let's look at coefficients and subscripts a little more closely so we get a stronger understanding of how we don't cross over between subscripts and coefficients in terms of balancing chemical formulas. We use subscripts. Chemical reaction equations, we use coefficients. We don't cross over. So if we had just C written down, we know that that means that we have just one atom of carbon. If we have just O written down, we know that that represents one atom of oxygen. O2 means that we have two atoms of oxygen in one diatomic molecule of oxygen. CO means that we have one carbon atom and one oxygen atom in a molecule of carbon monoxide. CO2 tells us that we have one carbon and two oxygens, and we have a molecule of carbon dioxide. If, however, we put a stoichiometric coefficient of 3 out in front of CO2, we know that we have 3 molecules of carbon dioxide. Each molecule of carbon dioxide contains 2 oxygen atoms and 1 carbon atom. And if we look at the 3 total CO2s, we know that we have 3 carbons and 6 oxygens. We would never write this as C3O6 using the subscripts to show this. The reason we would never do that is because this compound would be called tricarbon hexoxide. And as far as I know, there is no such compound as tricarbon hexoxide. When we read these subscripts, we can read them either at the atomic level or we can read them at the molar level. And so reading this balanced chemical reaction equation at the top of the screen, we could say that we have 4 solid aluminum atoms reacting with 3 gaseous oxygen molecules to produce 2 formula units of solid aluminum oxide. Or we could say 4 moles of aluminum react with 3 moles of oxygen to produce 2 moles of aluminum oxide. Now we know that we couldn't say 4 aluminum atoms react with 3 moles of gaseous oxygen to form 2 formula units of aluminum oxide. And the reason we know that we can't mix these two that way is because to go between particles and moles, we need Avogadro's number. So if we're saying we have moles, we're going to stick with stoichiometric coefficients that are representing moles. If we're saying we have atoms, molecules, and formula units, i.e. particles, we're going to stick with stoichiometric coefficients that tell us we have particles. If we ever want to cross over between particles and moles, we use Avogadro's number, 6.022 times 10 to the 23. The following chemical reaction equation here tells us that propane gas is going to react with oxygen gas to form carbon dioxide gas and water vapor. But it tells us nothing about the amounts of those species that are going to react. We know the states, the physical states of matter, and we know each chemical that's going to react, but we can't really use this chemical equation because it's incomplete. It's not balanced. We need to be able to go into the lab and calculate what amounts we need in masses in order to conduct a reaction or a chemical experiment, because we can weigh masses on a balance, but we have to know how many moles of a substance we have, or how many molecules or how many atoms, in order to determine what the mass would be. When we look at balancing a reaction equation, again, we're determining a way that we can add the same number of atoms to each side of the arrow. So in this particular reaction, where we have propane reacting with oxygen gas to form CO2 and water, and we recognize this as a combustion reaction, we're going to start with carbon, because we see that we have carbon in only one compound on each side of the arrow, and that makes it simpler to work with. We're going to work our way up to those species that are more complicated, and they're more complicated because they're going to be impacted by the earlier changes we make in terms of balancing this reaction equation. On the left, we see that we have 3 carbons, while on the right, we see that we have only 1 because there's no subscript right here. So that tells us we have only 1 carbon. To balance this, we're going to put a 3 out in front of CO2. And you can see why we're saving oxygen for later, because putting that 3 out in front of CO2 means that we've impacted the oxygen that we have. The next atom that we're going to balance on each side of this reaction equation is hydrogen, because hydrogen occurs in propane on the left side and only in 1 compound on the right side, water. There are 8 hydrogens on the left side. There are 2 hydrogens over here on the right side. So to balance this, we're going to put a 4 in front of the water. Now we have 8 hydrogens on both sides of the arrow. And lastly, we're going to look at oxygen. We look at oxygen last because, as you can see, by adding this 3 stoichiometric coefficient and this 4 stoichiometric coefficient, we've influenced the number of oxygens we have in both of those compounds. In fact, if we look at CO2, we have 2 times 3, which gives us a total of 6 oxygens. And if we look at the water, we have 4 times 1, because there's a presumed 1 there, giving us a total of 4 oxygens. When we add those together, that gives us a total in the products of 10 oxygens. Over in the reactants, we have only 2 oxygens. So to balance this on both sides, we're going to add a 5. And now this reaction equation is completely balanced. Let's look at something like photosynthesis, where we have CO2 reacting with water to form glucose and oxygen. Now, I want you to look really closely at this reaction. And right now we're looking at the forward reaction, but if we look at the reverse reaction, in other words, a reaction in which we would be forming CO2 and water, we can see that glucose reacts with oxygen to form CO2 and water. In other words, glucose is a fuel. And the reverse reaction here is a complete combustion. So if you're trying to write photosynthesis in your bio class, you just write it as a reverse combustion reaction. And you should be able to do that now, because you know that fuels always react with O2 to form CO2 and water. Let's balance this reaction as we see it, and let's start with carbon, because carbon shows up in CO2 on the left side of the arrow and shows up in glucose on the right side of the arrow. Over here, glucose has 6 carbons, and on the left side of the arrow, we see we only have 1 carbon. So we put a 6 in front of the CO2. Next, we'll look at hydrogen because it shows up in only 1 compound on each side of the arrow. Over here in the products, we have 12 hydrogens, and over here in the reactants, we have only 2. So if we put a 6 in front of this water, we have 12 hydrogens on both sides of the reaction arrow, and now we'll turn to oxygen, which is a little bit more complicated because it shows up in all 4 of these compounds. Over here in the reactants, we see that we have 2 times 6, which gives us a total of 12 oxygens. And then we have 6 times 1 for the water, which gives us a total of 6 oxygens. And now we know on the left side of this reaction arrow, we have 18 oxygens. Looking at the products, we have 6 oxygens in glucose, and we have 2 oxygens in O2. So that's only a total of 8. So we need to increase these number of oxygens that we have on the product side. Now, since we have 12 oxygens in glucose, and I can tell you we don't want to make any changes here. And the reason we don't want to make any changes here is because if we do, we're going to change the number of hydrogens and the number of carbons that we have. And we're going to have to make an adjustment then on the left side. It'd be much better if we could just add a coefficient to the O2 that would take care of balancing this reaction equation. Again, we need 6 so that we have 18 on both sides. So that means if we put a 6 in front of the O2, we now have 6 plus a total of 12, which gives us a total of 18 oxygens on both sides, and this reaction equation is balanced. Let's look at something a little bit more difficult, and we can see that this is a combustion reaction because we have butane, which is a fuel, reacting with O2 to form CO2 and water. Again, a typical complete combustion reaction. We'll start with carbon because carbon shows up in 1 compound on each side of the arrow. We see that on the left side of the arrow we have 4 carbons, and over on the right side of the arrow we have only 1 carbon, so we put a 4 in front of the CO2. We'll turn to hydrogen next, where there is 10 on the reactant side of the arrow, and over here on the product side of the arrow we have 2. To get 10 hydrogens, we need to put a 5 in front of the H2O. And now we're down to the oxygens. Over on the reactant side, we have 2 oxygens. And if we calculate what we have on the product side, that is 4 times 2, which gives us a total of 8 oxygens. And then 5 times 1, which gives us a total of 5 oxygens. And so we have a total on the product side of 13 oxygens. The problem is that 2 does not divide into 13 evenly. And so how do we handle this situation? Well, we could put 13 halves as a stoichiometric coefficient. The reason we can do that is because 13 halves times our 2 oxygens. You can see that the 2 will cross cancel, and we'll be left with a total of 13 oxygens, which is what we have over on the right side. So that will only work, though, if we handle every other stoichiometric coefficient the same way by multiplying through by 2. So if we do that, that means we're going to get 2 butanes, and then 13 halves times 2, we've already looked at that, and that means that we're going to have a total of 13 O2s on the reactant side. And then if we multiply the 4 CO2s, we're going to get 2 times 4, which is a total of 8 CO2s. And then if we multiply the 5 H2Os, we end up with a total of 10 H2Os. So let's erase the 2 out in front because we're done with this process and the brackets. And let's just go back through and verify what we have. So we have 2 times 4 gives us 8 carbons on the left. And over here on the right, we also have 8 carbons. For the hydrogens, we have 2 times 10, which gives us 20 hydrogens on the left. And if we look over here on the right, we have 10 times 2, which also gives us 20 hydrogens on the right. And now the oxygens. We have 13 times 2, which gives us 26 oxygens on the left. And over here on the right, we have 2 times 8, which gives us 16 oxygens in the CO2. And 10 times 1 gives us 10 oxygens in the H2O, which gives us a total of 26 oxygens on both sides. The last thing that we need to do is make a determination about whether or not we can divide out a common factor here. And so a common factor of 2, 8, and 10 is, of course, 2, but 2 is not a common factor of 13. So we cannot divide out a common factor, and so this reaction equation is balanced. This brings us to chemical calculations because once we learn how to balance reaction equations, we can use the stoichiometric coefficients to do chemical calculations of those chemical reactions in the lab, so we can make determinations about the mass that we may start with or the mass of the product that we may indeed end with. You know already that if we want to go from grams of A to moles of A, we're going to use molar mass, because molar mass includes both of those units, grams and moles. Similarly, if we wanted to go from moles of A back to grams of A, we would use molar mass. Also, if we want to go from moles of substance B to grams of substance B, again, we're going to use molar mass because the molar mass contains the units grams and moles. And we could go from grams of B back to moles of B, again using molar mass. We would just flip the conversion factor appropriately so we can cross-cancel. If, on the other hand, we want to go from moles of substance A to moles of substance B, or from moles of substance B to moles of substance A, we cannot use molar mass because we don't need a conversion factor that contains grams. We need some conversion factor that contains moles of substance A and moles of substance B. So we're going to use the coefficients in the balanced reaction equation as our conversion factor to go from moles of one substance to moles of another substance that are involved in the same chemical reaction. So let's look at this problem. It's asking how many grams of nitrogen. So right away, we know that we're looking for grams of nitrogen. are required to produce. So right away, we know we're producing ammonia. That's our product. And we want to produce 7.50 grams of ammonia in this reaction. We know that we cannot go from substance A to substance B without molar ratios from the balanced chemical equation. So we're going to have to write the balanced chemical equation to perform this reaction calculation. So step 1 is writing that balanced chemical equation. If we don't know anything else, we do know that NH3 is the product. When we look at NH3, we see that it's composed of only nitrogen and hydrogen. So those have to be our reactants. So we have nitrogen and hydrogen reacting to form ammonia, or NH3. We also know that nitrogen and hydrogen are diatomic molecules. So whenever we enter them into a balanced reaction equation, we have to show them with the subscripts 2, because that's the way they're found in nature, which is why you had to memorize Honkelbrith or have no fear of ice cold beer. Now this balanced chemical equation, it's not balanced yet. So we look at the left side and we see we have 2 nitrogens. On the right side, we have only 1 nitrogen. We fix that by adding a stoichiometric coefficient 2 out in front of ammonia. But when we add that stoichiometric coefficient in front of ammonia, we've changed the number of hydrogens to 6. And on the left side of the reaction equation, we only have 2 hydrogens. If we put a 3 in front of H2, we now have 6 hydrogens, and now our reaction equation is balanced, and we can use it to do calculations. So number 2, we're going to use these molar ratios. Number 3, we're going to convert those molar ratios into some kind of conversion factor that we can cross-cancel so that we can get from one substance to another substance, substance A to substance B. So we start this calculation with the only data value we have, which is 7.50 grams of NH3. And we let that guide us because we know we don't want grams of NH3 because the problem is asking us for grams of nitrogen. So grams of NH3 is going to go on the bottom so we can cross-cancel it. We know we have to get to moles or we can't use the mole ratios from the balanced reaction equation to go from substance A to substance B. So we use molar mass to get to moles of NH3. We need to know the grams. And so we know that nitrogen is 14.00 atomic mass units, and we have 3 hydrogens, and so that's 3.03 atomic mass units, giving us 17.03 atomic mass units, which we know converts directly into grams per mole. So our grams per mole, we already have the molar part in the numerator. We put the grams part in the denominator here. And we can see that we're going to cross-cancel grams of NH3. We have moles of NH3, and the question is asking for grams of nitrogen, so we know we're going to have another conversion factor, and in this conversion factor, moles of NH3 is going to have to be cross-canceled, so it goes in the denominator. We can use our balanced reaction equation now to go from moles of NH3 to moles of N2. So we put moles of N2 on the top. And then we look at our balanced reaction equation. We say we have 1 mole of NH2 because it's invisible. So we know that the stoichiometric coefficient is 1. And we have 2 moles of NH3. We enter those mole ratios to give ourselves a conversion factor in the dimensional analysis. Now we know that we're going to have another conversion factor because we've cross-canceled moles of NH3. We now have moles of N2, but the question is asking for grams of N2. We know how to get to grams from moles. We use molar mass. We know that the moles of N2 have to be on the bottom. And we know in 1 mole of N2, that would be 14 times 2, giving us 28.00 grams of N2 per mole of N2, which is the molar mass of N2. And I have to use N2, not just nitrogen, because I have N2 in my balanced reaction equation, and that's what I represented in the molar ratio in the previous conversion factor. Now I've cross-canceled moles of N2. I have grams of N2, which is grams of nitrogen, and all I have to do is solve this problem. So it's going to be 7.50 times 28, and then I'm going to say equals, and then divided by, because I want the product that I'm going to divide by. I open my parentheses again because I'm dividing by an entire product, and I put in 17.03 times 2 and solve. And I get a long number, 6.165590,135. And again, this is grams of N2. And now I can look at my significant figures. The only data value I have is this 7.50 grams of NH3 that I used, and there are 3 significant figures in that value. So 3 significant figures in my answer puts me here at the 6. I evaluate the next digit over. It's 5 or greater, so I have to increase the last retained digit by 1, giving me 6.17 grams of N2 for my final answer. Now you notice that here in the solution, the problem is being worked out step by step, but in the final answer, the entire dimensional analysis is shown to you in one calculation. It's all written out together because this is what gives you the most accurate answer. And I want to point out to you that the answer here is 6.18, where we got 6.17 grams of N2 when we worked this out. Have a look at the molar mass, the grams in the molar mass of NH3. The rounding was different. And so because that rounding was different, that gave an answer that was different in the hundredths place. Now remember, I talked to you about this, how you could get different answers when you had different rounding, and you could even get different answers using different periodic tables. This is taken into consideration in chemistry. So where your math instructor is going to mark it wrong if it's off by 1 in the hundredths place, chemists know that periodic tables give different values for atomic mass units because of precision of the equipment that's used to derive the average atomic mass units for every isotope of a given atom, elemental atom. So I would never put on a test, for example, answer A is 6.17 grams of N2 and answer B is 6.18 grams of N2 because I know either one of those answers would be correct. Not unless answer E said A and B. So you don't need to worry about having answers that are going to be ambiguous like that. Let's look at another practice problem. This one is asking how many moles of carbon dioxide will be produced by the combustion of 30 moles of butane. And I'm going to help you with this one because of the butane. So we start by writing the balanced reaction equation because we know that we're going from butane to carbon dioxide. And that means we're going from component A to component B, or substance A to substance B. And the only way we can get between one substance and another is to use stoichiometric coefficients. So we'll use the mole ratio from the balanced reaction equation and then put it into a conversion factor that we can solve the dimensional analysis for. And the answer the publisher gets here is 120 moles of CO2. So let's work this problem out. We start with butane, C4H10. And we know that this is a combustion reaction because they told us. And so that means that C4H10 is going to react with O2, and it's going to form CO2 and water. The same path that all complete combustion reactions take. When we balance, we're going to start with carbon because carbon shows up in one compound on each side of this arrow. So we see that we have 4 carbons on one side, and we have 1 carbon on the right side, so we're going to put a 4 in front of the CO2. We move to hydrogen. We have 10 hydrogens on the left side and 2 hydrogens on the right side, so we put a 5 in front of the water, so that we have 10 hydrogens on both sides. And now we move to the oxygens. And this looks just like the same combustion reaction that we resolved a couple of slides back. We have 8 plus 5 gives us 13 oxygens on the product side, but we only have 2 oxygens over here on the reactant side. And 2 is not a common factor of 13. So we resolve this by putting 13 halves here. And we put 13 halves there because we know the 2's are going to cross cancel. But we have to multiply this entire reaction equation through. All the stoichiometric coefficients have to be multiplied through by 2. So that's going to give us 2 times 1 is 2 out here in front of butane. And 2 times 13 halves is going to give us 13 in front of this O2. And 2 times 4 is going to give us 8 in front of the CO2. And 2 times 5 is going to give us 10 in front of the H2O. And now we have a balanced reaction equation that we can use to solve this problem. So we start by writing down what the problem gives us, which is 30, and there's a decimal place. So both of those digits are going to count as being significant. We have 30 moles of butane, which is C4H10. We need moles of carbon dioxide. So we know that we don't want moles of butane, so we're going to put moles of butane on the bottom so that it'll cross cancel. We can use the stoichiometric coefficient to get from moles of butane to moles of carbon dioxide. So we put moles of carbon dioxide on the top. And we can cross cancel our moles of butane. We know that we have 2 moles of butane to 8 moles of carbon dioxide. And so we fill in our conversion factor into our dimensional analysis. The question is asking us how many moles of carbon dioxide, and so it looks like we're done. We just have to do the math. So 30, and don't forget your decimal because that means both of those digits count as significant, times 8 equals, and then we're going to divide that by 2 and get our total value. Which is 120, and that is 120 moles of CO2. Now we look at our significant figures, and we know again that we have 2 significant figures here in our only data value. So our answer has to have 2 significant figures, which puts us here at the 2. This 0 in 120 moles of CO2 doesn't count as significant because there isn't a decimal in that number. And so our answer is 120 moles of CO2. This is a your turn problem asking what mass in grams of H2O can be produced from 9 moles of O2. And so I'm going to leave this problem for you to work out on your own. That wraps up our lecture for reactions, balancing equations, and stoichiometry. As always, if you have questions, bring them to Chem at Night Mentorship, or definitely email me so that you can get your questions answered. We probably have another week or 2 before we start looking at exam 2.